Hello, this is the operating system class, and today we will be talking about the internal structures inside an operating system. This is the outline of today's lecture. As you'll see, we'll cover, as usual, a few topics from the operating system services, system calls, what are the types of system calls that exist, what are possible designs, trade-offs, and possible implementations for the internals of those structures. And then we will briefly look at what is a virtual machine and possible ideas on how to debug an operating system. The objectives of this lesson are three. First, to describe the services an operating system provides to users, processes, and other systems. Second, to discuss possible ways of structuring an operating system from the inside. And third, we will try to explain how operating systems are installed and customized, and how they basically boot. So first of all, an operating system provides some user interface. Basically, all of operating systems have one variation of either a command line, something that you type on a keyboard and you get some feedback, a graphical user interface, so you interact it through some drawings that appear on some screen, or they are batch systems into which you submit a bunch of commands and they got executed later on without any immediate feedback if you want. So this is the first service that an operating system provides. The second operating system service that we discuss here is regarding program execution. And this basically allow an OS to load a program into memory and to run that program, kill it or end its execution, either normally, so as if the computation that was required to do actually completes, or abnormally, maybe there is an error, there is a crash, a seg fault, or things like this. The third service that an operating system provides is regarding I/O operations. And this is because, as we know by now, programs might require to do some I/O, to write data, to read data from a net from some device. And this is a service that the OS is in charge of. And the fourth service is regarding file system manipulation. And this is because programs need to read and write files and directories, create and delete them, search for files, list metadata regarding those files, try to control who can access a given file, which group of users can do that. So this is in charge of one of the services that is implemented by an OS. In this drawing, we see a view of the operating system services. The services that we mentioned before are here. We see program execution, I/O operations, file system management, and of course, also execution and termination of processes, which could be here in error detection. As you see, there is those services sit below the system calls. We will see what they are. And above everything, we have the user interfaces that we mentioned before. Those services are used by the user and other system programs. There are other services that are offered by an OS. Now we look at communication, and this basically allows processes that are executed by the OS to exchange some kind of information either within the same computer or between computers over the network. These communications can happen over something called shared memory, or perhaps through another paradigm called message passing. In this case, these are both type of possibilities that exist, and we will look at some of them in more details in a future lecture. The sixth service that we look at is regarding error detection. And this is because the OS always needs to be aware of possible bad things happening. It may be there is some error in the CPU, error in the memory hardware, for instance, some bit flips. Some I/O might be failing, your SSDs perhaps are going to be not functional in a few cycles and need to be repaired, and DOS need to be aware of that. And for each of those type of errors, basically DOS needs to take some action to ensure that the system keeps running, and then you have some consistent result. And the way to detect and possibly react to those errors are most of the time given by possible debugging tools that allow programmers to catch and possibly fix those errors in time. And the last set of services that we look into this lecture are all related to what we call resource sharing. So we have one that relates to resource allocation. And this basically happens when you have multiple users or programs or processes running concurrently. And the resources must be allocated to each of them in a fair manner. There are many types of resources. Some of them we mentioned during last lecture, such as CPU cycles, main memory, and others. Others might have special requirements, and others maybe have some special types of requests that need to be handled. The next type of service, this is the 8th that we see in this lecture, is regarding accounting. And basically, is a service offered by DOS to keep track of which user is using resources, for how long, and what kind of those resources are being used. The 9th and last service that we see in this lecture are regarding protection and security. And this is because owners of some information are stored in a somehow can be stored in a multi-user setup. Imagine a machine where you have more than one user, and DOS wants to control how those informations are being shared, who can access those informations, and for how long. So there are in place services that relate to protection and to security. There is a subtle difference between these two. So protection basically involves ensuring that all accesses to a system resources is controlled. You know exactly what is going on. Instead, security of a system basically tries to protect access to some resources from outsiders, perhaps requiring authentication or some kind of key management, and also to try to defend some devices from invalid accesses. One thing that we should remember is that if a system is to be protected and securely operated, basically you need to protect and install precautions more or less through all the system. And as we used to say, a chain is only as strong as its weakest link. So as long as there is one possible way to break, the attackers will try to go there rather than the most secured and protected parts of OS. The command line interface, or sometimes we refer to CLI, is basically a command interpreter and allows you to type direct commands to the OS. It's possible that this command line is implemented directly in kernel. Sometimes there are system programs that do this for you. There exist many possible flavors. Sometimes those are called shells. On Linux, for instance, there are several pre-installed options that you might heard or you might want to try. The TC shell, the bash or burn against shell, the Z shell, it's one modern option. This is the one that I use, for instance. And the way they primarily work is all the same. They try to fetch some kind of program from a user and they execute it. Sometimes the commands are built in, as it was in the past, and sometimes they are just names of programs, as it is in the case of GNU Linux. What is nice is that if you are relying on a system like GNU Linux, if you need to add new features, you don't have to modify the shell itself, because you just have to have the program installed on your machine and you can use it directly from the command line. And this is how it looks like if you're using the bash the bash. You can see you have a bunch of outputs here. Here you see some details regarding the terminal that you're using. In this case, this is the name of the user. This is the root, the administrator. This is some information regarding the name or the host name of the machine that you're running. This is the timestamp at which this command was given. Of course, it's an old image, but it's still valid. It works exactly like this today. And here you see how you can simply execute some commands. You type this command here, swap -sh. It gives you some details from asking the kernel, some details regarding some specific part of the memory, in particular the swap memory in this case. Or you can type this other command, uptime. It gives you since how long the machine is been running. As you see in this case, the machine was recently rebooted. It's only up since 9 minutes when at the time where the screenshot was taken. There are 3 users running, and it gives you also some statistics regarding the load of the machine in the last 1, 2, and 5 minutes. Now, it's possible that more recent versions of shells change the frequency of those timestamps or time samples. So maybe this is not 1, 2, and 5, but could be 1, 5, and 10, or 1, 10, 15. But anyway, the concept is the same, and you can find this information by trying to read the help command for a given command. You might try -h after the command, or trying man uptime as another additional command. As we mentioned before, the other possible way to have an interface is through some graphical metaphor. Usually the most common one nowadays is the one of desktops, as we know by now. So there are some peripherals that you can use, mouse, keyboards, some kind of monitors. There are icons that represent files or programs or some actions. You can click on an icon and this triggers a sequence of commands, for instance. And what you might not know that this kind of metaphor was implemented and invented many years ago, by now I would say 50 years ago, at Xerox PARC in California. And nowadays many systems basically include both, and you get to be familiar with both basically if you want to become somehow an expert user of an operating system. Each of the OSs have their own names, their own variants, their own different specificities, specific features for a given graphical interface or for commands, but in general, they all look somehow similar. Here we see some of the names that exist for somehow modern operating systems. And just to give you another example of what a graphical user interface might look like, this is taken from macOS 10. It is also, I would say, 10 years old nowadays. The most recent version of it is somehow similar, apart from some graphical cosmetic features. But here you see some windows here. You see applications running like a calculator. You see you can browse through some icons here that points you to some hard disks, for instance. You might have pictures of some kind. You might get other types of applications like an address book, like in this case. You might have additional system if you want system utilities, like having the time of the day here and other statistics regarding the workload of the machine. But of course, every OS has its own, let's say, metaphor of how to represent these concepts in their own graphical user interface. The concept is not to know all of them, but to know that this way of using a machine exists, and I'm sure by now every one of you knows this. So now we go one step deeper. As you remember from slide 5, we have all the possible GUI here, or the command line at some level here, and below we have the syscalls. See in page 5 for the full drawing. So the syscalls or the system calls basically represent the programming interface to the services that are offered by the OS. Most of those services or this programming interface is accessed via some high-level API rather than calling directly the system calls from a program. The way you usually do this is through some, for instance, standard C library as the one that we commonly find in all the OSs. There are the three most common APIs are the Win32 APIs for Windows, the POSIX APIs for POSIX-based systems. These basically include all versions of Linux, all versions of Unix, and all versions of macOS. And there is also a Java API, which is basically the way for the JVM or Java Virtual Machine to access those services. So one question that we might ask is why to use an API rather than directly the system calls. So one good answer is that if you are relying on an API rather than using directly the system calls, is that you are adding some genericity to your program that allow you to move or to port more easily your program from one OS to another. So in this example, we see what is the sequence of system calls that are issued or executed to copy the content of one file to another file. As you see, it's a long list, and you will see that even for small operations, this list can be quite long. And these system calls are used or necessary to acquire the input file name, to write some prompt to screen, accept some input, open the file, and if the file doesn't exist, abort, create the output file, then do some loop reading the content of the input file and copy it to the output, and so on and so forth. And if everything goes okay, then terminate normally. If something breaks, like if the file doesn't exist, and if something else crashes, it terminates abruptly. As an additional example, we consider the read file function from the Win32 API. And this is a function that is used to read from a file. As we see, the signature of the API is as follows. There is some function name, there is a bunch of parameters, and there is a return value. In this case, it's a Boolean, whether true or false, basically. There is usually in the documentation, we'll find a description of the parameters that you need to pass to a given system call. In this case, we see that there is some type of handle for the file that one need to read. There is the buffer where data will be read into. There is the number of bytes that the read file call has to read. This is a word. And there is also the number of bytes that the read call has read during the last read, so during the previous one. And there is some other Windows-specific parameter that relates to overlapping I/O. So in general, you will find this set of descriptions for a given system call: the name, the return type, the set of parameters with their types. And this is how you can start using a given API for an OS. But the API is somehow a high-level description of the system call. How is this implemented for real by an OS? So typically there is a number that is associated with each system call. It's a unique number. And you can imagine that there is a kind of table for which those numbers are indexed and associated with the specific piece of code that has to be executed. The system call then, what it does is to invoke the intended function inside the OS kernel and return the status of the system call, whether it succeeded or not, for instance, and any return type return value if there was a result to be sent. We will see that this operation, this type of sending results is driven by something called software interruptions or trap. We will see this in a future lecture. What is interesting, and this is why the system calls are convenient, is that usually the caller, which means the programmer that is using the system call, doesn't need to know how the system call is actually implemented. You need to know whether the call obey a given API and to understand what the OS will do and what will do as a result. And this is good because you don't need to become an expert of all the possible kernel details just to open a file, for instance. So for instance, as a user application, you are writing a program that needs to open a file here. You will just call this function. Then the system call moves from the user mode, this is where your application is running, into the kernel mode. And now it's the turn of the kernel to execute the corresponding implementation of that system call. So this, you can imagine, is the system call index. That will find the implementation of the operation open. You can imagine this is the integer in position I that gives up to the OS the position of that code. And now the OS knows that for this system call, it needs to execute all this code. And once this is completed, the return goes back via the system call interface back to the programmer. For instance, suppose you have written a very simple hello world program, as the one that you see here. There is a main function, there is a return 0, everything has worked, and then somewhere you have a printf. So a printf is your first system call, and you know that it takes one parameter, optionally. Once you execute this piece of code, the process moves from user mode to kernel mode, and the corresponding implementation of the printf system call results in the execution of the right system call, the native one, in this case in a Linux Unix system. Once this is executed correctly, the return goes back and the execution can continue from here. So most of the time, the amount of information that is required to execute a given system call is more than the simple name. Usually you need to pass some parameters to execute a given system call correctly. So there are three possible ways to pass those parameters to the operating system. The simplest one, this is the first one, is to pass those parameters inside the CPU registers. And in some cases, there may even be more parameters than registers. So what do you do? The second possibility is to store them in what we call a block or a table directly in memory. And then you can address, and then you pass the address of that block as a parameter in a register. This is what Linux does. And then there is a third option, is that you put those parameters inside the stack of the given program that you are executing, and then you pop those parameters off the stack by the OS. This is what Windows does. The interesting part is that the second and third approach basically allow you to not limit the number of or the length of parameters that you can pass to a given system call, which is instead the case for the simplest scenario where you cannot pass any number of parameters. So let's see how parameter passing works. This is the option 2 that we have seen in the previous page. Suppose that you have X as parameters for a given call. What you do, you put X into a register here, you load this, and then you know that you need to execute system call 13. So now the system call will know that it needs to load its parameters from table X, and then X will be fetched from here. One thing that it is of our interest in this course is that is to wonder what is the relation between system calls and Java. And as you might know, Java is not specific to a given OS or a given platform. You write some Java code and it's supposed to run more or less everywhere where there is a JVM. What is interesting is that the Java bytecode, which is the compiled version of your code, is translated to machine code on the fly by the JVM. So that basically means that many Java calls that you do in your program are implemented below the scenes by the JVM directly into OS calls. And then inside the JVM, then there you see that there are some calls that are really system specific and that are not very generic as the ones you would implement yourself as a programmer. And this is why there are specific versions of the JVMs for each operating system, one for the Windows, one for Unix, etc., and so on and so forth. It is, however, possible to use machine-specific code even from within a Java program, and this is by using the native keyword, which you might find, for instance, if you look into the code itself of JVM. And in normal programs, it's more rare, but can be done. For instance, you would do this if you need some very specific optimizations or to access very specific devices. Of course, if you do that, then your Java program becomes no longer portable, which is one of the main reasons to use Java. So this is something to keep in mind when you are programming with Java. So there exist a few types of system calls that as programmers we need to know and to use. Some of them relates to process control, some of them relates to file management, others regarding device management and manipulation. Some of those are used to communicate, as we mentioned earlier, for instance, via shared memory or message passing, and others relate to protection. It's possible most of the time to find somehow mappings between the system calls that exist on a given OS and the same ones that exist on another OS. It's, as we see in this table, most of the time the names are a bit different, and so one needs to know and be somehow expert in the specific OS that you want to use to understand exactly what is the system call that you need. But as you see, there are calls for the same groups, same types of system calls for both OSs. Here we don't see other OSs, but they are there. So in the case of file management, there are basically common system calls that are used to create and delete files, read and write content into those files, perhaps move data or move files to other locations, setting attributes, whether a file is readable, only executable, can be read and write, things like this. Of course, you have either those to set those values or only to read those values. And all those system calls are really redirected to the actual implementation for the specific functionalities of file management. And this is the main role of what a file system does. We will look into file systems in a future lesson, but especially in modern operating systems, there are a bunch of options that are either pre-installed or that are easy to add to a given set of to the ones that are already available in your OS, and you can use one or the other according to your needs. I mentioned here the few names that you might know or read before: X3, X4, BetterFS, and others. Other examples are those related to information maintenance. You can imagine that those are used to transfer information, let's say, between the operating system and the user program. So to understand what is going on. For instance, you want to know the time of the day, you want to know the current name of the user, or also to monitoring calls. Perhaps you want to know what are the running processes in a given OS, how much memory is left, and things like this. On Linux, there is a special directory, that is the directory proc, and in there you will find a bunch of details that relate exactly to this. You will find internal details of the OS as in the form of a file. So as long as you can read that file, you will get access to those informations. For instance, what are the processes running and how much memory is available as a file inside the directory proc. These are also, there are also a bunch of other system calls that are important to debug the OS. For instance, there is one that is called single step that allows the CPU to issue a trap, so an event that says, okay, I've executed one instruction, let's stop for a moment and let's see the state of the system as it is now, the state of the memory, state of registers, and so on and so forth. And this is useful, for instance, when you are debugging a given program that you know that will crash at some point and you want to know exactly step by step what is going on. This is exactly the type of operations that a debugger does. If this trap is caught by a debugger, this event basically is caught by a debugger, the debugger will be able to show all those details. Another example of system calls regards communication. Basically, the kernel provides means, tools, or APIs for processes to exchange information of some kind. And this is basically can be done along two different paradigms, message passing and shared memory. In the message passing paradigm, there is basically something attached to a process that allows that process to receive messages and to send messages. This something is called a mailbox. And through message passing, one has to issue calls to locate a given destination, establish a connection, read or write data, and wait until a given message arrives. In the case of a shared memory, you can imagine that there is a process 1 and process 2 here, and then there is a shared area here where they try both to read and write at the same time. Of course, this immediately leads to issues with synchronization, that you need to be sure that those processes access that shared area in a proper and consistent manner by using specific protection mechanisms to prevent race conditions. We will see all these in a future lecture as well, but this is just to give you an overview of the possible system calls that exist and a few examples. Now we start looking at how a given process can be created, and we do this with respect to an old but still valid example of single user monotask operating system, which is the MS-DOS. In that system, there was basically only one program at a given time that can be executed. This includes the command interpreter. So once you issue some command there, the command interpreter was somehow put aside and your program was running at its place. This was designed for very low resource computers. You can imagine the 8086, which date back to the 70s or something like this. There was a very simple method to run a program for MS-DOS. This is the one that was used at those times. Basically, the operating system was loading the program code into memory. Doing so, it was erasing a large part of the shell code. And then the entire free memory was available to the process. So there was basically no sharing among other processes that were using the same machine. This simple method was also setting the instruction pointer to the start of the program code. Basically, it was pointing the processor to the first instruction of the program so that it could start from there. And then there was a very small portion that was used to resume and restore overwritten portion of the shell. And this was happening upon the call to the exit system call. So here on the left side, we see the system at startup. And here we see the system while it is running. As you see, there is a fixed area that is used by the kernel. And then a portion of the memory that was used by the command interpreter is basically removed, freed, in particular this part here in this example. Here you see it is freed, and the process can allocate all this memory for its execution. And the free memory, of course, is reduced while the program is running, while the process is in execution. In the BSD operating system, it was instead possible to run, it is possible to run multiple programs at the same time. As you see, there is still the kernel here at the bottom of the memory. There is still some free memory, but then, and you have multiple processes, B, C, and D, and there is an interpreter that is always running there. So now the free memory can be shared across the various processes. So in the previous slide, we mentioned BSD or FreeBSD. So what is it? It is a Unix-based operating system. It supports multitasking. And that basically means that the command interpreter or the shell can continue to execute while there are other programs running. There are multiple programs that reside concurrently in memory. And then there is the process of the creation of a process follows a specific sequence of system calls. There is a fork, there is also can be an exec and an exit. For the fork system call, there is a new process that allocates new memory space in free memory. How this memory allocation operates is the topic of chapter 8 in a few weeks. Then the system call exec will actually load the program code and will start its execution. And finally, the exit system call will terminate with a given error code. Conventionally, 0 is if there is no error, or other values will indicate a specific error. There are also system programs that are the way that users actually relate to the OS and that try to understand and study what is going on inside an OS. There are many types of system programs, and they can usually be divided in the categories that you see here regarding file manipulation or providing status, support for different programming languages, options to communicate, or other types of application programs. The system programs, they basically provide a convenient environment for programmers to run and execute. Some of them, as you will see, are basically simple user interfaces over system calls. Others can be much more complex than what a simple user interface program could be. There are programs that are, for instance, related to file management, and that are specialized to operate on files, so to create or copy content on files, so to rename them, to print the content, to dump lists of the content of a directory, and things like this. For what concerns status information, some system programs are basically optimized to ask the OS for specific information, such as the date, the time of the day, how much memory is available, and so on and so forth. And others are related to specific performance metrics, or perhaps gathering debugging information, or even the system logs. Typically, these programs, what they do is to output their results either on a terminal, let's say on a screen, or even to files, so that those output can be later on studied and analyzed. There are other types of system programs. Some of them relate to file modifications, and those we are very familiar with. You can imagine those are the text editors that we use on a daily basis to edit our files. There can be special commands that maybe some of you have used to search content inside files, or perhaps search specific pieces of text inside large files. If you are familiar with the command line, maybe you know what a grep is or what a set is. Those are system programs that are used to fetch or find content inside the file and to replace it, for instance. There are system programs that are specific to programming languages. So these are the compilers, the assemblers, the debuggers, the interpreters for a given program. As you will see in Java, some of them exist and some others are not. So not all languages have all the tools that are mentioned here. There are system programs that are dedicated to load and execute other programs. So you can imagine that there are loaders, there are linkers, and other system programs like that. And then there are other type of system programs that are dedicated to communication. For instance, they are able to establish, let's say, virtual communications between processes so that they can share messages. Or, for instance, to send messages from one screen to another, or even, of course, to send emails, or to log into a given machine remotely, such as the SSH command that some of you might know, or to transfer file from one machine to another, either, for instance, in a secure manner, for instance, using the system program SCP. So there are many. Now, one important topic that one needs to understand and study is how a given OS, a given design, can be actually implemented. Now, this is a quite difficult problem, but there are several approaches that have been proven successful during the history, and some of them we will look more in detail. And this is why the internal structure of a given OS can vary very much from one example to another. The possible way to start designing an OS is to define specific goals and specifications that you want to match for your OS. And of course, this is also something that needs to go more or less side by side with the choice of the hardware on top of which you want to run. As you know, there is a specific OS for a given hardware. We know that, to give you an example, the macOS runs specifically on hardware that is specifically designed for that OS. So there has to be a specific support from the OS to run on that specific hardware. There are more or less two categories of goals that one needs to consider when designing and implementing an operating system. There are those that are somehow user goals, and others that are system goals. From a user point of view, an OS should be convenient to use, easy to learn as well, reliable. You want your OS to work every day and every time, and more or less continuously. It has to be safe, not causing harms and not producing any damage, and also fast. Let's say, for instance, you want it to be interactive. But then there are the system goals. And the system goals for an OS are that it should be easy to design somehow, should be more or less easy to implement, but also to maintain, especially if you are dealing with a vast amount of code. You want this to be easy, or as easy as possible. You want this to be flexible so that if there is a new functionality, it is easy to add and to switch from those functionalities, for instance. You want this to be reliable. So if a given functionality works today, it should also work tomorrow and the day after that. You want this to be bug-free or error-free. Somehow you should implement your design that in a way that is correct. And you want your OS to be efficient, as we said also in a previous lecture. You have a bunch of resources, and you want them to use. You want your OS to use those resources in the most efficient manner. So one important principle that needs to be considered when dealing with the design and implementation of an OS is the one of separation. There are two things that you need to consider: a policy, so what will be done by the OS, and the mechanism that will implement that policy, how that what will be implemented. The mechanisms basically determine how to do something, and the policies will decide what will be done. And this separation is actually quite important principle and allows basically as much as flexibility as you can when taking the decisions that can then be changed at some point in the future. So let's once again consider a very simple structure for an OS. MS-DOS was in particular written to provide the most functionality in the least space, in the least memory space that was available at the time. It was not divided into modules, so not so much flexible. So although there was some structure inside, the interfaces and all the functionalities and all the different levels of functionalities were somehow intermixed. In general, there was a layer structure where we had the BIOS, where the firmware was installed here. Then there was some MS-DOS specific device drivers that was using the BIOS. Then there were system programs that were dealing directly with the BIOS. And then there were also application programs, the ones that were actually installed, that were either relying directly on the BIOS or also using a more layered approach to try to use first the resident system programs that were then dealing with the device drivers. So it was a somehow layered structure, but there were also means to bypass those layers to go through to the bottom one if need to. So in the previous example, we basically have seen a kind of a layered approach where you have the OS that is divided into a number of levels or layers, and each built on top of the lower one. Usually the bottom one is the hardware or layer 0, and the highest one or layer N, depending on how many layers you have configured or the OS is designed for, is the user interface. With the modularity, layers can be selected so that each uses functions that are given from the lower level layers, so you don't have to rely on the above ones. There is also a bunch of drawbacks. First, that calls must traverse all the layers. You have many layers here. A call might need to traverse all of them to do some operations. This is usually a cost, some kind of overhead that you need to pay. It is also not easy or necessary or even possible to separate the services into layers. Sometimes some of them are dependent from each other, and maybe you have kind of loops or possible strange interdependencies that make this layered approach very challenging or even very difficult. And in this drawing, we basically see what we just described before, where we have the hardware level at the center, and then whenever you have to reach an outer layer, you are crossing boundaries at this point that make possible. Of course, this is done in the two directions, and the transition between layers is what causes most of the time the overheads that you can observe in your applications. Another example of a system that is somehow simple in its structure, sometimes we refer to it as monolithic, is the traditional Unix system, in which We have some kernel interface at the bottom that interacts directly with the hardware here. And here it knows basically the underlying hardware, the memory controllers, the device controllers, and even the terminals. Then we have a bunch of system calls, as the ones we have seen already before, and some others that deal directly with the kernel here. Then we have the shells, the system programs that we mentioned before, as well as some other system libraries. For instance, the libc is here. And then we have the programs at the very top, the user level programs here. As you see, this is also kind of a monolithic approach because the separations are, okay, they are drawn here, but sometimes it's difficult to discern between one element and also to which exact level or layer that program belongs to. So as we mentioned Unix in the previous slide, let's see what it is. First, Unix was the original US operating system name, but now it's more of a family of operating systems. Unix is limited by hardware functionality, but the original Unix operating system had somehow a limited structuring as the one we have seen before. In general, it consists of more or less two parts. We have the system programs and the kernel. So the system programs is exactly as the other examples we have seen before. Instead, the monolithic kernel has everything that is below the system call interfaces. So it is somehow more complex and in a way potentially more difficult to maintain. In particular, this provides a lot of the services that we mentioned before. The file system, the CPU scheduling, memory management. Basically, all those functionalities are all implemented at the same level, the same depth in the stack that we have seen before. On the other side of the spectrum, we have what we call a microkernel architecture, which instead try to move as many functionalities as possible outside the kernel, but rather into the user space. And then there is a kind of a communication mechanism between the different user modules that rely on the message passing paradigm that we mentioned before. So first of all, this has a lot of benefits. It is easier to extend. It is easy to port the OS to new architectures, new type of processors, new type of memories, and so on. It is more reliable because there is less code actually running in kernel mode. And when you are running in kernel mode, you are dealing, you remember you have the user mode and the kernel mode. And when you are below, when you are here, whatever you are doing is somehow dangerous and dealing with low-level functionalities that need to be very, very reliable. It is also more secure. And there is, for instance, one of the most famous microkernel implementations is called SEL4. It has actually been proven to be secure using formal methods. So this is a way of statically verifying that the code is correct and it operates the way it's supposed to be in all the possible conditions. The downside, as you see, it's always the case that when you are dealing with possible design trade-offs, you have to consider the benefits, but also the downside is that if you are moving a lot of functionalities into user space, then it means that you are moving continuously from user space to kernel space, and this has obviously a cost that usually has an effect on the performances of the OS. Nonetheless, the microkernel architecture is the one that is used by Windows or was used by Windows NT and perhaps more recently macOS. So in the case of macOS, as we mentioned before, we have the application environment and the common services. For instance, the system programs are here. And then there is a lower level microkernel here that also relates on a set of utilities that are given by the BSD environment. All the interaction happen between these two main components, and this is where the majority of the overhead comes when dealing with these kind of architectures. Now, when dealing with additional functionalities, most of the most recent kernels implement modules. These allow programmers to use an object-oriented approach to provide new functionalities. So that means these are easier to implement. Each of those modules is very well separated from the rest. It's well isolated. And then also the way those modules talk to each other and to the kernel are very well established, defined since the beginning, and are all the messages, all the exchanges are happening over known interfaces, so over specific calls. So it's easy to monitor, to control, and to react to possible problems. Every module is usually loadable as needed, and once loaded, it's available into the kernel. So overall, the idea is somehow similar to layers, but just more flexible. So this is, for instance, the case of the Solaris OS, which is yet another operating system. Here we have the kernel, and then we have a bunch of modules that provide different functionalities. So there was a module to handle file system, a module to deal with device and bus drivers, others to deal with scheduling operations, and so on. So far we basically dealt with physical machines, but what are virtual machines instead? So a virtual machine basically takes this layered approach that we discussed before to its logical conclusion. It basically treats hardware and the OS kernel as if they were all hardware. So in a way, a virtual machine provides an interface that is identical to the underlying bare hardware, so that you can emulate somehow the presence of a given CPU or a given device. And the OS hosts, so the one that is running the VM for you, basically creates the illusion that a given process has its own processor and memory and disk and so on. And instead, this is all being virtualized, as we say. Then each guest is provided with a given copy of the underlying computer, and this is a virtual copy, and this is what the VM is, a virtual copy of the underlying computer. What are the history of VMs? By now, what are also its benefits? They were firstly introduced already back in when there were the first IBM mainframes in the 70s. And now they are, of course, largely used in cloud computing environments. They are basically a way to multiplex different execution environments over the same hardware. You see, you have a VM1, a VM2, and then here you have the same hardware for all of them. The VMs basically also allow to protect the execution of one program or even multiple users from each other, allows to share files between them in a controlled manner, which is good. It's also useful for development and testing of programs. You might want to try a given program on a specific setup. Maybe you want a VM running a specific Linux distribution, Ubuntu, and then you have another VM running Windows, and then you want to try to see if your program runs on both operating systems. And if you have such a setup, it's easy to test and check how the program behaves on those environments. It is also a way to somehow consolidate the many low-level resources into fewer, busier systems. So you have, instead of having many machines that are only lightly loaded, you try to consolidate many virtual machines into fewer ones, and that they can take advantage of the real physical properties in a more efficient manner. There exists let's say a common format, a standardized format for virtual machines, and these basically allow to run a given VM across different host platforms. It means that you could prepare a VM on your, let's say, Linux guest, let's say your Linux guest machine, and then you prepare this VM, and then you have your colleague that has a Windows guest, a Linux host machine, and then you can give your colleague your VM, and this VM will run here on top of a different host OS. So it's a way to share, if you want, different virtual machines across hosting platforms. So more precisely, the structure of a virtual machine with respect to a non-virtual machine is as follows. Here we have the hardware. On the left side, we see the non-virtual machine. You can consider this as bare metal. You have some hardware, and then you have the kernel and the processes, as we have seen before. Now, what we have here is the same hardware, can be exactly the same. Then we have some virtual machine implementation. We will see some of them perhaps. And then you have the VM1, VM2, and VM3. And what are those? Those are, once again, those are processes. You can see they are the process running a given VM, which inside run its own kernel. And the kernel of VM1 is completely isolated from the kernel of VM2 and from the one from VM3. And also the set of processes that are running here is different than the one you have here and the one that you have here, because those are completely separated environments. And to give you an example of a concrete implementation of a virtual machine, maybe you heard before about VMware, which is a very well-known provider of virtual machine implementations. And as you see, this is the example of a VMware architecture for a Linux host operating system. So below this level, below this layer, you see the actual hardware devices, the CPU, the memory, I/O devices. Above this, you have a virtualization layer, which is provided by VMware, on top of which you are running 3 different VMs. One of them is running BSD, another one is running Windows NT, for instance, another one, an old version of Windows. And inside each of them, they have their own set of applications or maybe even one. As you see, you can use, in this case here, we are using 3 different VMs, but next to it, on the same machine here, on top of the same machine, there are also regular applications that continues to operate exactly as usual, without basically knowing that next to them there are full-blown virtual machines. Now, of course, when dealing with virtual machines, you might have heard, or by now you maybe have guessed, that the JVM is the Java Virtual Machine. It consists on a set of programming language specifications. So this is the Java language. Then you have an API that is implemented to talk to the runtime. And then you have the virtual machine specification itself for the Java runtime. This is the VM. So how the JVM differs from what we have seen before? The JVM is basically what we call a runtime, so a program that is able to execute programs. Those programs are implemented in Java and then are compiled into a specific format. These are the .class files. So those are the ones that are provided by us, the users or programmers. Then there are the Java class files. These are the ones, for instance, available in the JDK. These are given to us by the providers of the JDK, the programmers at Oracle or the community around the other implementations of the JDK. So all those classes are loaded by something called a class loader inside the JVM. And then there is a Java interpreter that can execute those programs. Now, all of this is basically running on top of a host system, be it Windows, Linux, or others. Exactly as we mentioned before with respect to the plain old, to plain virtual machines. They run some kernel and processes and what other processes on top of a virtualization layer. So this, if you want, this all of these can be all considered as a kind of a virtualization layer that allows us to execute Java programs. What is interesting is that by having .class files, one can basically deal with a simple version of the binary format, the .class, and then that class can be executed by multiple implementations or different or specific implementations for specific host OSs, Unix or Windows or Linux here, or others. You can imagine Java platforms implemented in hardware, for instance. So how do we go from having simple Java programs into the class files? So this is the workflow of users that want to use the JDK. Basically, we deal with a bunch of .java files. For instance, here we have 1 and 2. Those are compiled by the Java compiler, and the Java compiler produce a bunch of .class files, in this case, 2. This is basically the compile time environment that is offered by system programs, a compiler. In the case of Java, this is Javac. Then we need to somehow move those .class files, which is basically ship the bytecode, the compiled form of our programs, into the runtime platform, the JVM itself. These files, the .class, need to be transferred into the JVM, perhaps simply moving files into the right location, or perhaps sending them through the network. And once they reach their runtime, they are loaded, as we have seen before. They are somehow combined, or they use the .class files that come with the Java API, and then they are executed. So this is how the JDK is used in combination with everything else. And where is the separation between the JDK and the runtime, the Java runtime. The two remaining topics that need to cover during this lecture are related to debugging and boot. So first we look at debugging. Debugging is basically the process of finding and fixing errors, or sometimes called bugs. Most of the time, operating systems, they generate what we call log or log files. And in there, we can find information related to the error that just happened. Sometimes applications that are somehow failing or crashing, they generate a core dump. And what they do, they capture the state of the memory of that given process, so that can be analyzed later on. There is also the possibility to generate a crash dump, which is basically the representation of the kernel memory at the time of the crash. So one is for the process, the core dump, and one is for the kernel, the crash dump. And beyond crashes, what is usually done to optimize performance is what we call tuning or performance tuning. One thing that is useful to know or somehow interesting is that there is basically a good chance that debugging is twice as hard as writing the code itself. So basically, it's a quite funny quote. If you write a code as cleverly as possible, you are by definition basically not smart enough to debug it. And in a way, it's actually unfortunately true. Usually, debugging is much harder than debugging it. There are, of course, many different tools that can be used to the support programmers to debug. One of them, for instance, is dtrace. It gives you the sequence of system calls that have been issued so far. So there are also other tools that allow you to somehow, what we say, live instrument the current execution in a way that you can attach your debugger to a running process and try to understand at runtime what is the state of the registers and seeing what code is being executed and perhaps trying to identify problems or even potential performance bottlenecks. And finally, we cover the last part of this course, which relates to the generation or the booting step. So in general, operating systems are designed to run on a machine on a given class. The system must then be configured for each specific computer site. You need to know exactly what is the underlying hardware that is available so that you can actually boot.
So there is a program that is called sysgen that is used to actually obtain the information that is required to generate the specific configuration over which the OS is going to boot. And then there is a phase called booting that is basically the computer itself starting up, and then what it happens here is that it loads the kernel itself into memory. There is a difference between booting and the Bootstrap program, because in the Bootstrap, the code is actually stored in the ROM, which is this read-only memory that is always available even upon reboot. And the Bootstrap itself, the Bootstrap program is the one that is actually able to load the kernel, the code of the kernel, load it into memory, and then start its execution. So basically, the system boot works like this. We know that there must be an operating system available so that the hardware can use it. And usually this is a small piece of code, which is the Bootstrap loader. And this piece of code is capable of locating the kernel, loading it into memory, and starting it. So this is the job of the Bootstrap loader. And sometimes this is a two-step process where basically the boot block at a given fixed location loads the Bootstrap loader. So it's a two-step, if you want, process rather than having directly the Bootstrap loader capable of loading the kernel code. The last step that is missing is basically what happens when you actually click the start button on your machine on your laptop. The way it works usually is that the execution always starts at a given fixed memory location, and this memory location is somehow written and permanently written inside the firmware. And the firmware itself is actually also in charge of holding the initial boot code that is then able to go to the Bootstrap loader or to go to or to load the location of the boot block. So this was the last slide for today's lecture. I hope you enjoyed, and we will see each other quickly through a WebEx session to discuss possible doubts you have regarding this lecture, or instead you will go to the lab.